Hello everyone. In this series of Vibrational Dynamic course, today's class is about damped free oscillation. In real life, the oscillation will be reduced by friction, and the oscillation is gonna die out after a certain time. And this phenomena is called damping. So the damping is a phenomenon by which the damper is gonna dissipate the energy of oscillation. And this damping device can be called a damper, which can use a viscous damping, like this one in here. And this damping system consists of piston cylinder system. And in between there is a fluid in here. Okay, the fluid has a viscosity by which is going to reduce the motion, okay, or the velocity of motion of a mass. Okay, and one example of these dampers is the shock absorber, which we can see it in any car. Shock absorber. You can see it in here. It has the same system of the piston cylinder, and it has a liquid inside, maybe oil, maybe air. So by which if you make a tensile force of this system, the piston is going to move very slow, or if you compress it the same way. So if you compress it, it's going to slow it down as well. So this is why it's called shock absorber. So for this system, which is spring damper mass system, we'll have a different equation of motion compared to the one we have studied before, which is free and damped oscillation. So today we'll have just a brief about how to determine the equation of motion for a damped free oscillation. So there is no applied force in this system. Remember, the force is equal to 0, or the excitation force is going to be 0. So let's try to find the equation of motion for this system. Let's derive it together. We will just apply the same way we have done for the previous classes. So what we are going to apply in here, we are going to apply Newton's second law. Okay, Newton's second law. Newton's second law. Okay. So it will be the summation of all forces acting on the mass should be equal to the mass multiplied by the acceleration. Let's make it dot notation x double dot. Okay. So if we draw the free body diagram of this mass, right? So as this mass is going to move to the right, as we indicate positive coordinate or positive direction of this coordinate in this direction, then what will happen? There are opposing forces acting over that. The first force, which is the spring force, okay, which is act against the motion of the mass, right? And the second force is going to be now the new force, which is the damping force. Okay? damping force. Let's call it FC. So spring force, it's gonna be minus K multiply the displacement. However, the damping force, it should be minus C. The term C is the damping coefficient, right? Multiply by, it's not the displacement, but it's gonna be the velocity, and that noted by X, the single dot. Okay. So, and now, how can we apply Newton's second law? So the summation of all forces should be mass multiply acceleration. It's going to be minus K or minus C, or let me make it FC plus Fs. And that one would be mx double dot. It's going to be minus Cx dot minus Kx. So if we move this one to the left side, you will get the equation as m double dot plus Cx dot 1 minus or plus Kx, which is the displacement, should be equal to 0. So we determine the equation of motion of this system, and this system is a single degree of freedom. Okay. And this equation, it's nothing but second degree ordinary differential equation. And we can solve that equation right by the general mathematical methods. All right, but normally we can apply the complex notation to solve this problem, right? So, or to solve this second degree ordinary differential equation. Let's make shorthand notation for, if we divide all of them by m or by the mass, what you will get. So if you divide it by the mass, you will get it as x double dot plus c over m x dot plus k over m x equal to 0. So let's assume that, of course, omega naught squared should be equal to, as we remember before, the natural frequency of the system. Omega naught squared would be nothing but k over m. And then let's say c over m as gamma. Gamma is going to be c over m. Right? So therefore, the equation, this equation, it's going to be like x double dot plus gamma x dot plus omega naught squared x equal to 0. So now we have this equation, right? So system will oscillate at a frequency or less than the natural frequency, and this oscillation will die out. Okay. So to solve this equation, we can convert it to complex number. Okay. Complex number z. So complex number. So let's assume to solve this equation, we may use complex number z, right? So therefore we replace x by z. Okay. X by z, and now our equation will become z double dot plus gamma z dot plus omega naught squared z equal to 0. And z, as you remember from the previous class, we have it as amplitude E for the amplitude E or exponent of j, and will be pt, which is as plus, let's call it alpha, right? Alpha. So let's assume it this way. So this is the complex number z. Okay, now if we would like to know what's z dot or z double dot, we will do just the rate of the complex number, and the second rate or second derivative of z is gonna z double dot. So z dot is gonna be equal to dz over d time. Let's have it the first derivative of the z is gonna be what? It's gonna be, now we have this product, so we have a number a multiply x. Let's call it, if f is equal to a multiply x and a is a constant, so the rule is we'll have a multiplied by the, so I mean the derivative of the function or the equation f is going to be equal to a multiplied by the derivative of x or the first function x. So what we will get, a is a number, then it will be left in here, and the derivative of exponent. So for example, if f is equal to ex, all right, then what the derivative of the function is gonna be, or f prime is gonna be e x multiplied by the derivative of the terms over the exponent e. So what you will get, we repeat e j pt plus alpha multiply the derivative whatever up in here, it's going to be j and pt. Okay, so the derivative of t is going to be 1, so this one will be p, and j multiply the derivative of alpha, which is constant, will be 0, and the derivative will be 0 will be 0. Then therefore we'll get it as a j p exponent of j pt plus alpha. Okay, but remember, a multiplied by this term, this is a, and exponent of jpt plus alpha is only the complex number z, and that one become jpz. Okay? jpz of this. So this is what? Z dot. Okay. What about the z double dot? Will be the second derivative of that. And so let's have the derivative of this one. So z double dot, it's gonna be the derivative of this term. So a j p will be remaining the same. Multiply this one plus alpha, multiply the derivative whatever in here, then what we'll have jp, and JP what you will have for JP would be, if we multiply it, what you will get, A J double dot J squared P squared E power J PT plus alpha. But remember what we have studied in the last class, that J squared, what it will give us will be square root of -1 all squared, and that one will give us -1, right? So the value of that J squared will be -1, and Z double dot, it will become a minus P squared, and A and this term will be Z. Okay, so we'll have minus P squared Z, right? So now we have determined what's Z dot, what's Z double dot, and also what the function Z is. Therefore, if we would like to substitute all of these in the general equation, this one, which is Z double dot plus gamma Z dot plus omega naught squared Z equal to 0. So you just substitute Z dot and Z double dot, then we will know what we are going to get in this equation. So let's make it. So we'll have a minus P squared Z plus, then we have Z JPZ plus omega naught squared Z, and that one become equal to, oh, we forgot gamma here. So we have a gamma, with gamma multiplied by Z, so don't forget to write gamma J, gamma J P Z omega plus omega naught squared Z equal to 0. We have a common factor as Z in all of that, then we'll have minus P squared plus gamma J P plus omega naught, right, multiplied by as Z equal to 0. All right. So to solve this problem, Z is it's not gonna be equal to 0. Cannot be 0 because this is the displacement. This is the, so this one cannot be 0. Z cannot be 0 because it's the term of oscillation cannot be equal to 0. And also if we think about gamma, remember gamma is the, if cannot be 0 because we have a damping. If there is no damping, then gamma should be equal to 0. Then all the terms in here, this term should be equal to 0. What about P? Okay. What about P? Is the term for the trial function. Okay. Okay. This one is we need to make it as a complex number by which we can solve this equation. Okay. So generally the P can be written as a complex number, which is the natural form n plus JS. Okay. So then we will try to find what P squared, and then we substitute inside this equation, then we can find the solution. So p squared, so it will become, let me rewrite it, p squared, it's going to be n plus js multiply n plus js, just squared. So what you will get? You will get n squared plus 2j ns plus s, or minus, it's going to be minus squared, minus s squared. How we do that? To explain that one, just let me redo it. N squared, n multiply n is going to be n squared, n multiply js, then what you'll have? Njs plus another njs, then this one multiply this one, what you'll get? A j squared, s squared, and then n squared plus 2njs. J squared is minus 1, then we are left with s squared. This is how we could get it. Okay, so this is how we find p squared. Now we'll plug in the p squared and p in this equation, and then let's substitute first, then we'll plug it inside this equation. And we equalize the okay, sorry for the inconvenience. Now let's find what's omega p or omega bj, which is in the equation, as in here it was omega gp or omega pg, and that's equal to, will be omega j multiply p, which is, what's p we have in here? N plus js, and that one will become, omega is gonna be we'll have omega jn plus omega j squared s. Then what you will get? You will get as omega j, this one is gonna be minus 1, then we'll have omega jn minus omega s. So this is what we have. So we have p squared and omega pj, and we have already we can substitute or plug them in this equation. Right, we multiply it by z then. So therefore what you will get in here, so we will have minus p squared, right? So minus p squared, you will get it as minus n squared minus 2n js and plus s squared. Then we have gamma jp, it's going to be plus gamma jn minus gamma s, right? Then what we are left with, plus omega naught squared, right? So that one equal to 0. So we have to equalize or multiply by z equal to 0. Z is not equal to 0. Then we have to equalize the real part to equal to 0, and imaginary part equal to 0. So where is the real part? We have real part in here, okay, this one and this one. So, and imaginary part, we have it as this one, okay, two things. So let's equalize the imaginary part. Equal to 0, therefore minus 2n js plus gamma jn equal to 0. So if we would like to determine the s, okay, what you will get s, we move this one to the other side, s is gonna be gamma jn divided by nj, or 2nj. N with n will be cancelled, j with j will cancel, then we have gamma over 2. Gamma over 2, and this is s. Right? We determine s. We need to find n now. So we equalize the real part and to 0, and if it's necessary, we substitute s in the function. Then the real part will have minus n squared plus s squared minus gamma s plus omega naught squared equal to 0. Remember, s is by gamma over 2. So, and minus n squared plus gamma squared over 4 minus gamma s plus omega naught squared equal to 0. If we'd like to determine n, then what you will get as n squared is going to be, you move this one to the right, and this one become omega squared over 4 minus omega s plus omega naught squared equal to 0. Oh, sorry, it's not equal to 0. Now, we focus on also this s. Sorry, this s should be omega over 2. So what we'll have? We'll have omega squared over 2, and also in here we'll have omega squared over 2. So let's have a common factor, which is omega squared. 1 over 4 minus 1 over 2, you will get it as minus n squared will be minus omega naught squared minus omega squared over or gamma squared over 4. Right, so we have it, and therefore if you'd like to determine n, will be the square root of omega naught squared minus gamma squared over 4, sorry, 4, and this is the solution for n. We have s, we have n, and now we can substitute that one in the general equation of complex number z. Complex number z. Okay, so z, as we know before, it is amplitude multiply exponent of j, okay, nt, or n, which is pt, right? Pt plus alpha, right? But p is what? Will be nt plus j st, right? So p is n plus j. This one will be n plus js. Therefore, it's going to be a exponent of j pn, oh sorry, it will be n with the time, n multiplied time plus js time plus alpha. Alright, so then we need to know that we move this one JAST, okay, as JAST is the imaginary part of that one, and that one will be the damping or rate or the decay ratio. So we'll have e to power j squared, j multiply will be j squared st multiply exponent of j nt plus alpha, right? So this one j squared will be minus st and exponent of j nt plus alpha. As we know, and we know, we just substitute the same number, what we have gotten here, n. So, and if we know that n is going to be equal to the damping frequency, n is the damping frequency of that, then it is going to be omega d in here. So you just substitute omega d instead of all of these terms, and s will be gamma over 2, sorry. So what you will have, a es is minus gamma over 2, right? So as we know, gamma over 2 in here, and n will be multiply t, then exponent j, n is omega d multiply time plus alpha, right? So now we have the complex number z in here, and if we would like to find the solution for this function, we will have it, which is the displacement at any time. It's going to be the amplitude of this one, the amplitude A, right? So multiply, so this one can be cosine and sine, okay, cosine and sine. So this one will be xt e to power minus gamma over 2t, and this one will be cosine omega d t plus gamma. Right, so this is the solution for this equation, and remember, this one will be the decay exponential, okay, this is the decay exponential, so decay which can be determine the damping, okay, which can, because the decay exponential of the damping, okay. So let's stop for a moment. Okay, so we found this equation, which is the solution of a oscillation, okay. So you can know the displacement at any given time. If we have a damping in the system, then, which is this one, right, then we will have a die out of this oscillation. So the amplitude is going to reduce until it's going to stop at a certain time after number of cycles. So for instance, in this diagram we can see that the free oscillation, okay, free damped oscillation of the system, if it is mass spring damper system, right? So that one is gonna oscillate, okay, at a frequency which is equal or less than the damping frequency of the system. Then we will have the oscillations curve will be something like this. So if you can see in here, for the first cycle, so at amplitude, which is the maximum in here, until this point, which is the first cycle, we can see the displacement become smaller, okay, and it's going to be smaller to the next cycle. Let's call it, this is cycle number 1, and this is cycle number 2, and this is cycle number 3, okay. So and we can see this dashed lines in here. It's nothing but the decay of the oscillation, which is this one, right? So this one. So we can determine that one if we know what's gamma. So what's gamma at any given time, then we can know the slope of this damping or this decay. All right, let's do an example, right, which can be found in the handout provided by the by UE Bristol. So let's read the example. A locomotive car of mass 2000 kg traveling at a velocity of 10 meters per second is stopped at the end of some tracks by a spring damper system. So we will have a car which is connected to the spring damper system. If the stiffness of the spring is 40 Newton per millimeter, and we have the damping constant C should be 15 Newton second per millimeter. Find the equation, right, of xt representing the motion of the locomotive car when it hits the buffer. So first thing we need to know before we make the equation of motion, we have to find gamma term and the damping frequency. Right? Let's do the gamma. Gamma is, as we assumed before, it is the damping coefficient over the mass. So the damping coefficient is given as 15 Newton second per millimeter, but remember we have to make it as in SI unit. Therefore 1000 should be multiplied by 1000 millimeter to find it as a meter. Okay, therefore then this one we divided by the mass, and the mass of the car is nothing but 2000 kilogram. All right, so what you will get, 1000 cancel, we'll have 15 over 2. Okay, and that one will give us as, we'll get a result of a value 15 over 2, and that's 7.5 second to power minus 1. Why second to power minus 1? Is, as you know, 15 Newton second per meter. It's nothing but Newton is kilogram meter per second square. Okay, Newton, so Newton will be kilogram meter per second squared multiply what? Second divided by what? All divided by meter. Okay, so meter with meter will be cancelled. Second will cancel and we are left in here. And if we divide that by the mass, which is 2 kilogram, we cancel with a kilogram, then we are left with 15 over 2 or 7.5 and the unit second. Okay, second, 7.5 second to power minus 1. Right, so 1 cycle per second. So 7.5 cycles per second. This is what gamma means. Right. The second part, we have to find omega d, which is the displacement, okay, or the damping frequency of the system. And if you go back to our derivation in here, damping frequency should be equal to this term, which is omega naught, which is the natural frequency of the system squared minus gamma squared. Okay, let's plug that one in here and find what's omega d. Omega d, it's going to be the square root of omega naught squared, and that will be k over m, right, minus gamma squared over 4, isn't it? Okay, so we know k is what? K, it's 2000, sorry, it's gonna be 40 Newton per meter, or it should be 40 multiplied 10 to power 3, which is 40,000 divided by the mass, which is 2000, right, and minus gamma, what we have found in here, 7.5 squared divided by 4, all under square root. This one will be cancelled with this. Then we have 40 divided by 2, it will be 20, and 7.5 squared, or the value, let's find the value immediately, and the value will be 2.437. The unit, of course, radians per second. So this is the omega d. Okay, to find the equation of motion, we have to set the initial conditions. For arbitrary constants are defined for the initial conditions in these equations. Let's say that the displacement at time 0 is going to be 0, and the displacement or the velocity at time of 0, as you see in here, once it's 10 meter per second. Okay. Find these initial conditions to complete the equation, and the derivative of this equation, okay, to simplify, it's given in here. Okay, it's given in here. But if we don't give you this one, we don't give you the hint, then you have to find the derivative of the equation of displacement. Okay, so find the initial condition or complete the equation, and the derivative will be in here. So what you will do, you will make the equation or the solution for this equation. So xt, it's going to be e to power minus, or e exponent of minus gamma over 2t, and multiply by cosine omega dt plus alpha. X, then when time equal to 0, then the displacement is going to be 0. Let's equalize this equation to 0. Therefore, we substitute t as 0, t 0 in here. What you will get, if t is equal to 0 at time equal to 0, what you will get, and then you will get this one as 1. Anything exponent to power 0 will be 1, and this one, if it's 0, then this one will be 0. Then we are left with A cosine alpha should be equal to 0. The amplitude of a displacement of free oscillation, it won't come 0. This one, it's not gonna be 0. Why? Because if you don't move the mass from its equilibrium status, okay, then what will happen? Okay, if you don't displace it, then okay, then what? Then it will not oscillate, right? So this is why we have to displace it. So A will never become 0, then cosine gamma or alpha is equal to 0. Therefore, alpha is going to be the arc of cosine of 0, and that is going to give us the pi over 2. Pi over 2 or 90 degrees, right? Therefore, we now know what's alpha as initial condition. If we substitute, okay, let's go for the velocity x dot when it is 0, what you will get. So when it's 0, so well, let's make it, let me rewrite the equation, and that will be x0, what you will get, A multiply the exponent of the time, it's going to be 0, then this one will be 1, then minus gamma over 2 cosine omega dt, here will be 0, then what you will get? You will get minus gamma over 2 cosine alpha minus omega d sine. Well, alpha is going to be, as we determined it, as pi over 2. Then we have this one becomes 0, and this is pi over 2 as well. Then sine of pi over 2 would be what? Would be 1. And this one will cosine pi over 2 will be 0. And this one will be 1. And that will the velocity should be equal to 10, isn't it? 10. So we'll have A, this one 0, multiplied by minus omega d equal to 10. Therefore, the amplitude can be determined by 10 over omega d minus omega d. But omega d is already determined in the previous section, which is minus 2.437. So we'll have 10 divided by minus 2.437. All right, minus 2. And that one will give us the value of the amplitude, which is minus 4.104. And that one must be amplitude in meters. Therefore, the equation or the solution for this equation should be, we just substitute the previous one. A will be minus 4.104 multiplied by the exponent minus the gamma is what we have found before. Gamma is 7.5. 7.5 divided by 2 is going to be 3.75 multiplied by the time cosine omega d, which is 2.437 multiply time plus alpha, which is pi over 2. And therefore, this is the solution for the equation of motion for the damped free oscillation. All right, that's all for about the damp free oscillation, and see you in the next class. Thank you for watching.